Welcome back to the podcast. And on today's show, we have a different guest from what often has come before. Mostly we talk with philosophers, as you probably imagine on the podcast. But today we have Flavio Del Santo from the University of Geneva, who works on the foundations of quantum mechanics. Flavio, welcome to the podcast.
Thank you very much, Jed. Thank you. Uh, yes, indeed, I'm a physicist. So
Yes.
yeah, well, most of my colleagues would probably indicate me as a philosopher or as a historian, but historians and philosophers think of me as a physicist. So I'm in this in-between ground.
Well, as a first question, then I might ask you just about that. How does your work intersect with the work of Karl Popper? We're going to speak a lot about his interactions with the foundations of quantum mechanics, but how did you come across Popper, and how did you come across his work, and how does it intersect with
Yeah.
the work you do in physics?
Yeah, so my intersection with Popper is quite broad, and it comes from different angles actually. So well, the main way I met the work of Popper was through one of his former students at the University of Vienna, from whom I took a course at in the philosophy department, and it's him who made me. So is Professor Milford, and he introduced me to the work of the logic of scientific discovery and against historicism. And then, at the same time, I was doing some research in the foundations of quantum, on the history of the foundations of quantum mechanics. And, and it was actually an anonymous referee of one of my papers on the history of foundations of QM in Italy that pointed out that Popper had some overlap with this. And then, I made 1+1, and then this Professor Milford sent me to Klagenfurt, which is a small city in southwest Austria, where at the Alpen-Adria Universität they have all the copyright of Popper and copies of all his correspondence. So the Popper's papers are there, and this started my journey into putting together my expertise in quantum mechanics, and I opened a new line of research to reconstruct what Popper did, something that I think is quite underrated and quite forgotten. So that his main contribution to the philosophy of physics and possibly to the philosophy of natural sciences altogether, it's really the foundations of quantum mechanics.
Well, let's get right into that then. I've got a few of your papers in front of me. You've written these incredibly lengthy, again, well-researched papers where you go into the details and letters and private correspondence between the two. So we're going to have to brush over some things in brief detail, but I think we'll nail most of the major topics, at least most of the major landmarks anyway. So Popper enters the field of physics. Quite early on, you mentioned his first book there, the Logic of Scientific Discovery, and he puts in there a failed experiment, and we don't hear from him. And again, well, that was 1934. We don't hear from him again entering the field until 1948, I think it is, after the war. So I might get you to take us from that failed experiment and to his re-entry into the field of quantum mechanics afterwards.
Indeed, yeah. So as you know, and some of the listeners to the podcast might know, Popper had a partial formal education in the natural sciences, in physics and mathematics in Vienna. He never completed that studies, but he was habilitated as a school teacher for mathematics and physics. And so he was always very interested, and his philosophy of science, so his general philosophy of science, his epistemology and his methodology is strongly influenced, as he multiple times acknowledged, by modern physics. So he had, while still a student or just after his studies in Vienna, he interacted with several physicists, who introduced him to both general relativity, and especially he got very fascinated by quantum mechanics, which was, let's recall that it was in its very early days. So quantum mechanics, we are celebrating next year the first century since the formalization of quantum mechanics that was completed in 1925. But still, well, first of all, nowadays we still don't understand it fully. We are still have very strong conceptual problems. And especially in the early 1930s, these problems, as you can imagine, were extremely new and extremely debated. And it is, in fact, in these years that the first textbooks about quantum mechanics appear. 1930, 31, 32 are the most famous first textbooks on quantum mechanics. Possibly the most influential, the one of John von Neumann, who introduced for the first time this collapse of the wave function in mathematical terms. And yeah, and it's at that stage that Popper enters for the first time this debate. Indeed, in his 1934 Logik der Forschung, so the logic of scientific discovery in its original German edition, he introduces this thought experiment aimed at showing that Heisenberg's uncertainty principle, which I may say a few words in a moment, was misinterpreted at best. So Heisenberg uncertainty principle is this fundamental principle of quantum mechanics that comes directly from the formalists, that if you have two physical observers that are called incompatible, you have, for instance, the momentum, so the velocity roughly of a particle, and its position cannot be known at the same time. So if you measure with better precision the position of a particle, its velocity, it's not your knowledge, but the knowledge that is available, let's say, of its velocity is lost. So there is really a linear correspondence between how much you can know about the speed and how much you can know about the position. And Popper devised this experiment, thought experiment, to show that Heisenberg uncertainty principle should not be interpreted in these terms, but these are just scattering relations. So is a not applicable to the single particle level as it was and is still interpreted nowadays, but it should be interpreted as an ensemble. So it applies to collections of particles. This was Popper's idea that lasted for well, I would say for most of his life. Only at the very end of his career, he got more into the single particle picture. But yeah, anyhow, these experiments turned out to be wrong. And Popper himself recalls these late, when he was 80 in his postscript to the Logic of Scientific Discovery in 1982. He remembers about this episode. It was a gross mistake for which I had been deeply sorry and ashamed of ever since. So this was kind of, so he entered the debate very early. He interacted with important physicists, including people of the orthodoxy like Bohr, Niels Bohr, one of the founding fathers of quantum mechanics. And yet he had this quite a bad start. And indeed, this prevented him from contributing further for at least a decade.
And after that period, so after the war is over, there's two conferences. I think one is in England and the next one is in Princeton in 1950. And that's in the presence of Einstein and Bohr, if I remember reading correctly. And he's trying to tackle the two-slit experiment, I believe. And he comes forward with the idea that probabilities need to be part of physical reality in some way. So I'll get you to take us to those two conferences immediately after the war, and what Popper, I suppose what the problem Popper is trying to tackle here with this experiment.
Sure. So Yeah, so after the whole mess of the war and Popper leaving Europe and devoting his time mostly to philosophy of social sciences, it is indeed in 1948, thanks to the encouragement of an important Austrian physicist, quite forgotten, Arthur Marx, from Innsbruck, who was actually the best friend of Erwin Schrödinger. Well, Schrödinger even had fun fact. Schrödinger had his first daughter with the wife of this best friend, Arthur Marx, but that's just gossip. And yeah, so Popper, also being an Austrian, starts having interactions with this Arthur Marx, who pushes him back into modern physics and quantum mechanics. And it is in 1948 that he gives a talk at the British Society for the History of Science. That's the first conference that you're mentioning. And another conference is at Harvard and in Princeton, where he in fact spoke about indeterminism in quantum and classical physics before Einstein and Bohr. So two giants of modern physics. So here we start seeing the delineation of one of the most important characters that would be central to the work of Popper in physics for the rest of his life, the concept of indeterminism. So if we are to crystallize the position of Popper about physics, you can say this is twofold and a quite innovative position, because usually these two positions are never met together. So Popper was a realist and an indeterminist. Let me explain what does it mean.
Yeah.
So realism is the assumption that there exists an objective physical reality out there. There is an outer world, and so it's at the ontological level, right? So then there is the epistemological problem, whether we can know and to what approximation can we know what's out there, but you assume that is not, so is opposed to idealism, subjectivism, solipsism. So you don't have, the world is not a creation of somebody's mind. It doesn't require have the interaction of somebody's mind, of consciousness, of an observer, but there exists an objective reality independent of any agent out there. So that's the position of realism that was very strong in Popper and in most of the criticists of the Copenhagen interpretation, as it were, of quantum mechanics. Because quantum mechanics seems to go in the opposite direction. You have an observer that is part of the narrative of the theory, and once the observer interacts with the system, is changing it irreversibly. So that's the standard story, and this was what bothering Popper and many others at that time, and still is nowadays. Is not a solved debate. The other term I used is indeterminism. So Popper strongly believed, and this was part of his general philosophical view, because he had also the same view against Marxism in the social and political sciences. Popper was convinced, and I'm very strongly with him on this, that events of the world are not predetermined. So if you have even if you have a full knowledge of the present state of the universe nowadays, imagine that you are like this ideal demon that Laplace invented in the 1700s.
Mm-hmm.
There is a superior intelligence that can grasp all at once every single degree of freedom, every single physical quantity that is relevant for the evolution of the universe. Even if somebody or something is capable of knowing all this, the future still is open. So there exists a non-trivial, a non-univocal correspondence between the present and the future. The present does not completely determine the future, but the future has some degree of openness.
Is this only applicable to quantum mechanics or classical physics as well?
Indeed. So this is so let's say at the mainstream level, physicists for the first time thought that this was a possibility at the fundamental level at the moment of quantum mechanics, because quantum mechanics only gives, really by the formalism, not due to some experimental mistake. And we were saying that quantum mechanics has been the first theory to induce physicists to think seriously about the problem of indeterminism. Before, indeterminism was considered only a, for all practical purpose, problem, in the sense that it was our limited knowledge of a system and not at the fundamental level there were indeterministic evolutions. So yeah, so that's the first thing, the mainstream story. However, Popper pushed this even further, and he thinks that also at the classical level there are systems that are not fully determined, and so the future is open even at the classical level. Something that just as an interlude, it relates to my current work in physics, where I'm also developing these ideas. So this is yet another influence, really at the scientific level, that Popper, you might say, had on my work with Nicolas Gisin at the University of Geneva, where we're actually developing models of classical indeterministic physics
I
using.
I read a
Yeah,
paper of yours actually in preparation for
yeah,
this. A fascinating one. This is a little bit of a divergence, but it's an interesting one, where you not only proposed an indeterministic future, but an indeterministic past as well.
indeed, indeed. So one of the aspects that we studied of the consequences of taking seriously this form of fundamental indeterminism is that even the past, under certain assumptions of finiteness of information, as we call it, so the assumption that uh, the universe is made of finitely many elements that can store only finite amount of information. Um, then we have a model or toy model, perhaps we don't claim that this is what actually happens, but we show that at least the logical possibility that the word um, is not only indeterminate in the future, but also the past at some point gets erased. And so somehow we are living in a slice of determined universe, slice, a temporal slice that can be very big, like we can remember perhaps billions of years, not us, but the universe can remember billions of years of its history, but not more. So that's yeah, a diversion, but I think relevant for the fact that Popper still nowadays has some influences on the current research
Mm.
in foundations of physics. Yeah, so coming back to the 1940s, there was this indeterminism in quantum and classical physics that really reprojected Popper into the debate on the foundations of quantum mechanics. And it is at this point. So before I was mentioning something. When I said indeterminism, I said the future is open to a certain extent. So what Popper started thinking at this point is that what does it mean if there is indeterminism? Because we don't live in a completely chaotic world, right? Like we can predict something. If I drop my pen now that I'm holding in my hands, well, it's quite deterministically falling on the ground, right?
Mm.
Perhaps it's not following always in the same way. Perhaps it's following slightly more on the left or on the right. But there are regularities that should be encompassed. So this degree, so this indeterminacy must be not an all or none feature. It's not just there exists pure randomness or fully determined events. There must be something in between. And this is what Popper started in the early 1950s, starting from 1953, actually. What the development of the conceptual tool that he called propensities. So propensities, they were just they became, first of all, it started developing this, but it's not until the late 1950s, in 57 and 59, that he started publishing about this. And these propensities are a very interesting, to me, conceptual tool. A propensity, as the English term suggests, is an intrinsic tendency, is supposed to be an objective um, tendency or propensity, indeed, for an event to happen, which is not deterministic. So a propensity is something that causally connects one event to another. If I drop the pen, then the pen falls on the ground. But then you can say it falls on the ground a bit left of my foot, with a propensity of a certain amount. So if the propensity is 1, it means that it's certain that it will do, and you recover determinism. If the propensity is 1/2, then it means that it's completely random, the outcome, if it will fall on the left or on the right. But then if you have a propensity of 75%, 80%, then you have a really an intrinsic tendency of the whole experimental condition. So it's a property both of the system and of its causal surroundings. The way I drop the pen, the gravitational field I'm in currently. So it's everything that can, in principle, influence an event to happen, that characterizes this objective property of the system, which, however, does not determine it in a full determinate way. It's not like it has a color blue, but it has a certain tendency of being blue or red. I hope that this is a concept that comes across quite understandably.
It does. I just have one. How's it different to frequencies? Popper held a different opinion beforehand, and then he changed his propensity. So what's the difference?
Indeed. So, first of all, Popper thought. So, it's a good question, because you're bringing me to some problematic issue with this propensity. So Popper introduced these propensities, thinking of quantum mechanics, thinking of indeterministic physics. So this was for him the right conceptual tool to analyze this, and I agree with that. And I think there is consensus on this. But he introduced this also as an interpretation of the probability calculus. So also Popper has been also contributing to the theory of mathematical theory of probabilities, also since the early days of formalization of probability. It was nowadays the most used axiomatization of probability is the one due to Kolmogorov, also in the 1930s. And again, in his The Logic of Scientific Discovery, Popper takes a frequency interpretation of probabilities. The frequency interpretation means that what is a probability is, so to define a probability, you need an ensemble of events that you can repeat. For instance, this dropping of the pen, and you can keep throwing the pen many times, and then you see how many times it falls on the left and how many times it falls on the right, and then you take just the ratio of the positive events, the events you want to consider, for instance, falling on the left, over the total amount of events. And there is a formal theorem that tells you that this frequency is called the Bernoulli's convergence law, or the law of large numbers. More repetitions you have of this event, the more it mathematically tends to be a probability in a formal sense. So it approaches a probability. What Popper wanted to do with propensities was to get away with this definition of ensemble. He didn't want any more to have this concept that you have to repeat many, many times something, but that you can associate to a single event, because you want to claim that this is not a collective phenomenon. It's not something that you have to collect, to throw multiple times in the limit of infinitely many times, the same dice, the same coin, the same pen on the left or on the right. But the concept was that quantum mechanics shows us that perhaps at the single individual level, you observe probabilities. You observe that the particle is behaving in different ways at a single individual level. Perhaps this is due to the fact that there is this kind of hidden non non-deterministic force that is pushing the particle towards one direction or the other. So it's really inspired by the fact that you want to describe at the individual level non-deterministic events and not as a collective. That's the difference with the uh, frequency interpretation.
Okay.
And
Yeah.
yeah.
Yeah, no, I think I've got my head around it. Yep.
Yeah, I can say more a bit more about the development of this, if you want, of this well, historically the development of these propensities, or perhaps you have other
Well,
questions.
perhaps we should push on to just trying to spread the story out a little bit. Perhaps we should push on to. You wrote that actually I think it must have been you have a quote here, which is Popper's most influential essay on the topic, and this is essay. I think it's called Quantum Mechanics Without the Observer. I think it's presented at the Colston Research Society after the Second World War. I could be off on that, but I might get us to walk forward to this idea. Popper says at the start he's trying to exercise the ghost called consciousness or the observer. And you mentioned Heisenberg's uncertainty principle earlier. And later on, in this paper, as you write, you say Popper is directing an attack against Bohr and Heisenberg's epistemology, and who advocated just that impossibility of observing a system without disturbing it. So, what is Popper getting at here, and why was it so important to him in so many ways that he's pushing this principle?
Yeah, thanks. Those are very good questions. So in yeah, just clarification. So 1957 is the Colston Research Society conference. Is the first time that he presents this idea of propensities. However, as I wrote in one of my papers, Popper was somehow quite disconnected from the community of physicists throughout the 1950s. So you have to think of this propensity interpretation the way so I'm talking at the sociological level here, really, but I think that's what's really important in the history of physics are collectives. And so in 1957 and 59, his first two papers on propensities were really just formal papers inspired by quantum mechanics, but definitely not too much related to the subject matter, and absolutely not read and appreciated by physicists, not even the ones that were good acquaintances of Popper. The paper you mentioned, Quantum Mechanics Without the Observer, indeed the most influential essay of Popper on quantum mechanics, it comes 10 years later, is in 1967, and is a paper that he writes for the first time, try to somehow expound organically his views on quantum mechanics. So that's really the first collection of his thoughts throughout several decades. They want to give for somehow his own interpretation of quantum mechanics. So this can be considered the first time that Popper really writes as a scholar dealing with foundations of quantum physics for physicists. Here, for the first time, you have the propensity interpretation not being merely an interpretation of probability theory, but being really an interpretation of physics, and in particular of quantum physics. The title of this paper, as you said, the Quantum Mechanics Without the Observer, and as you mentioned, this flies directly in the face of Heisenberg and Bohr, because what Popper calls is the great quantum muddle is that we are considering subjective elements that pertain to the observer as fundamental part of the theory in standard quantum mechanics, in the quantum mechanics that Heisenberg and Bohr have proposed. By the way, this is called the School of Copenhagen, or Copenhagen interpretation, which it doesn't really exist as a thing. Like there was never a unified Copenhagen interpretation. There is no such a publication where it is presented the Copenhagen interpretation. It's a collection of many, many founding fathers of quantum mechanics that share some features. And it's Popper that did more than anybody else to claim that they were all the same unified interpretation, all on the same page on a single interpretation. So it's somehow also I don't know if a merit or a bias of Popper,
Mm.
but somehow he had a very important historical weight. Popper also in this somehow in uh, putting together in the single bag many different thoughts about quantum mechanics that he was regarding as wrong. And the main factor of this that is in common to these interpretations that Popper calls the Copenhagen interpretation and that went down in history as Copenhagen interpretation is that you have complementarity between, for instance, particle and waves. So you have systems that behave sometimes as a particle, sometimes as a wave. For instance, an electron in the double slit experiment, and this is called the complementary behavior of a particle. Um, you have this intrusion of the observer, as Popper calls it, which is for the first time in physics, the observer is regarded as something fundamental. So you have some um, element which is not described directly by the theory that is necessary, nevertheless, to have a consistent story for the theory itself. So you need an external observer that does an observation, namely does a quantum measurement, and only then, only if there is an observer, then the reality that was indeterminate becomes determinate. So there is this jump from indeterminate to determinate due to the observer. And Popper could not accept this because of his, as we said, realism. So he wanted physical theories to be completely independent of any subject or agent or conscious being, and therefore his propensity interpretation comes to his help, right? So
Mm.
his idea is that these the reason why we see this passage from indeterminacy to determinacy is that there is this intrinsic tendency that is encoded somewhere in the word objectively independent of any possible subject, and it's these propensities that govern the whole universe in this indeterministic manner. So this is really the what these propensities is what help him achieve these this sought realism and indeterminism at the same time that I was talking about before.
How was this received by the broader community of physicists at the time? We haven't quite explained.
Yes.
I forget the phrase you used for the community of physicists that formed around Popper or with Popper inside, but a fairly dissident community. How was this solution received by the broader community?
Yes. So first of all, I should again stress that yeah, Popper really wanted to interact with physicists, really thought that these ideas were helping the conceptualization of quantum mechanics for physicists. It was not just quote unquote philosophizing in the sense of something that is kind of parallel and external, but he really thought that these foundational problems were helping the development of the theory. So I think he was quite frustrated throughout between this 1948 when he restarted doing physics until 1967. So he had 2 decades of being quite ignored by physicists. This is like a well-known problem, even in his Paul Schlipp Library of Living Philosophers volume on Popper, which is supposed to summarize the whole the comprehensive thought of a living philosopher. His struggles with foundations of quantum mechanics are not mentioned at all. There is not a single there is not a single article that portray Popper as a philosopher of quantum mechanics, which is quite telling. Anyways, this quantum mechanics without the observer indeed projects Popper instead back into this debate with physicists. The first to react are some of his friends, important physicists at that time, quite philosophically minded. One is Mario Bunge, Alfred Landé, who was a student in Göttingen, an assistant to David Hilbert, so people who were really very important in the early days of quantum physics. Bartel van der Waerden, who was a pupil of Emmy Noether, also in Göttingen. So they were really part of the entourage of the early days of quantum mechanics. They all reacted very positively to these quantum mechanics without observers. Interesting indeed, also David Bohm, who was the first one to create an alternative realistic interpretation of quantum mechanics, very celebrated physicist. He writes to Popper, I feel that what you have to say about propensities makes a genuine contribution to clarify the issues that you discuss, namely the foundations of quantum theory. And Bohm was even at the Colston Research Society conference 10 years before, where Popper, for the first time, presented his, in absentia, but still, he presented his propensity interpretation. But it's not until this quantum mechanics without the observer that propensities become somehow part of the physics debate, rather than just mathematical philosophy of mathematics, I would say, like foundations of mathematics, foundations of probability theory. So many good replies from very important physicists, let's say, after quantum mechanics without the observer, but also some criticisms. Jeff Boob, who was a student of David Bohm in London, and was to become a research assistant to Paul Feyerabend. He wrote the first rebuttal of these propensities and interpretation of Popper's. So he said that okay, the propensities are a nice idea, but they don't clarify anything about quantum mechanics, because still they conform to a standard probability theory, which is not the one that quantum mechanics tell us. Here it becomes a bit technical, but somehow he had a fair criticism. And yeah, so this has been the first strong criticism the Popper received. And soon after, there was the one quite notorious of Paul Feyerabend.
Let's get into Feyerabend actually.
Yes.
Yeah. So you've written a whole paper on this, and
Yes.
so I'll get you to introduce just who Paul. You mentioned him once already. Who was Paul Feyerabend? And yes. I guess how the relationship begins. Feyerabend, of course, has got a deep interest in physics even before he meets Popper, and the relationship is very typical of so many with Popper. It starts off incredibly well and turns out incredibly badly. So I might get to take us into that.
Yes. Yeah, so indeed, Feyerabend, as it is well known, he worked with Popper as I guess a senior student, you can say, in the early 50s, and Popper was really like the favorite pupil of Popper. Popper had a very, very high opinion of Feyerabend. Feyerabend was very, very dependent on Popper's, and this was Popper's ideas, and this was really how to say, was the beginning of a love-hate relationship that develops in a very crazy way, I must say. Like, reading their letters is entertaining and quite shocking sometimes. Like, their relationship went so deep, both at the personal and at the. It was really a drama. It was really a drama.
Mm.
So
yeah,
it started with this. It started with this big love. So 1954, Feyerabend published his first paper, Determinismus und Quantenmechanik, so determinism and quantum mechanics. And here he fully adheres to Popper's program. He weds he marries the thesis of indeterminism, even at the classical level. He doubts very strongly an impossibility proved by von Neumann that Popper was very critical of. So you find all the elements of being a strong Popperian in the foundations of quantum physics. Again, well, they have very good relationship at the beginning, still here, and then the problem starts slowly arising. So there is a first episode where Popper accuses Feyerabend of plagiarism. So in 1956, when Feyerabend publishes these notes on the impossibility proof of von Neumann, and Feyerabend published this in a very influential journal, Zeitschrift für Physik, in a German physics journal. And Popper writes to him in a very harsh, vitriolic way. So he writes that basically all the ideas that Feyerabend is expressing in that paper were stolen from himself, Popper, and his at that time research assistant Joseph Agassi. So he writes to, and here you start seeing that this very strange personal relationship they have. So I wrote in my paper that I indulged in some Sunday's psychologism of kind of framing this relationship as a preaching father and rebellious child. So at the beginning, they're very close to each other in the childhood, in the academic childhood of Feyerabend. But then at some point there is adolescence, teenage, and Feyerabend needs to be very critical of Popper, and Popper wants to really teach him lessons. Like it's really very interesting to. I mean, I don't want to reduce the whole scientific debate to this, but I think that these things, to do a good history of science, one should mention that science is made by human beings that have emotions and feelings and social interactions, and these play a major role in the way we do science. As a scientist, I acknowledge this, that this neutral, objective character that science is often attributed is only partly true. And I think that we should talk about these things. That's why I want to put a bit of emphasis on this kind of research I do, historical research I do. Anyways, where are we? Yeah. Popper writes to Feyerabend, I do, of course, agree with the content of your paper, since you got the complete contents here in my room from Joseph Agassi, and myself. In fact, we made the point much clearer and better than you do now in your paper. If you do not add a very careful acknowledgement to Josk and myself, it will be a flagrant piece of plagiarism. He writes to him directly like this. And a few days later, not receiving an answer, he continues, I do not believe that the content of your paper are really worth publishing. It is not that I think that you're taking valuable goods from me, goods which I find valuable. It is a different thing. It's a matter of principle. I shall express my view that I consider a publication morally wrong. I should have willingly agreed to have published by you, provided you would proceed in the proper way. I have to do it for your own sake. Otherwise, you will never learn what one may do and not do. So you understand what's the tone of the conversation here.
And it doesn't sound like the first time he's been through this with Feyerabend.
Indeed. And there is multiple of in this paper I wrote, you find multiple of these citations also to other people. And Feyerabend is always very condescending to Popper when he points out he apologized thoroughly, and he even accepted to add an acknowledgement note that was dictated by Popper, written actually by Popper. And then in the end, he prevented it from appearing in print. So he accepts from Popper, he takes the notes, he says yes, and then he confesses to his young friend's assistant of Popper to say no, but it was too strong. I didn't want to give in with. So there is this a bit of hide and seek game, and there is this kind of condescending and in the end not doing what Popper wants. And yeah, but so here we are still at the very early stage. Here is just somehow uh, you know these are small individual accidents, and it was still a very good relationship. So Feyerabend was still consider himself, I would say, a Popperian, or at least speak out, being vocal about critical rationalism in his lectures um, at Berkeley. He was teaching exactly using the same course that Popper would give. He was speaking on his behalf in conferences. He was really much into the Popper uh, entourage and very strongly supportive of Popper, except for a few of these accidents.
And
But
of
it's really
course,
with
as I
yeah,
just add, and of course, as you mentioned in your paper, even this is getting reported back to Popper through people like William Bartley, who are saying
indeed,
that he's stealing your
indeed,
lectures here.
exactly.
Mm.
So even these, I mean, these I have to say we should take it with a grain of salt. I really don't know. I mean, yeah, but indeed it was reported. So indeed there is the general feeling in the Popperian community that Feyerabend is a ungrateful Popperian.
Mhm.
He's a Popperian that is kind of using Popper's words without always telling that these are Popper's words. That's somehow the way that is perceived in the community of Popperians at that time. That's sure. And yeah, and Feyerabend even has this in multiple letters. You see this excuse where I say, I do not think that I even conscious. So I quote just one, but there is multiple of the same kind. I do not think that I ever consciously used your ideas without the proper acknowledgement, although it may have been the case that having heard them from you, I continued thinking, returning in a roundabout manner to these ideas I had originally gotten from you, but without knowing any longer that it was the case. And multiple times he says that he has thought so much of these original ideas of Popper that at some point he thinks it's these are his own ideas. This is
Mm.
what he multiple times write to Popper. That there is this kind of running into circles into acquiring the ideas of Popper very deeply and forgetting the source somehow. That's the main excuse that he uses throughout the years. At any rate, I
Mm.
think I think we should. Yeah, it's really later in the 1960s, and it's particularly due to these quantum mechanics without the observers that the paper of Popper that we mentioned in 1967, that Feyerabend starts the big war against
Yeah,
Popper.
that's
Yeah,
I might get you to just go into that a little bit more in detail before we
sure.
push on to the 1980s and finish it off.
Yes.
But it, at some point in this, one of the things that seems to upset Popper a lot is Feyerabend seems to find the need to defend the Copenhagen interpretation, or at least
Yes.
say that the people who are attacking it are attacking some sort of, I think the phrase he used was vulgarized version of it, and he accused Popper and people like Popper of making a straw man of a sort and just beating up on the
Yes.
interpretation. And and of course you're right, and this is interesting that through people like Bohm, because he seems to develop his methodological pluralism from this. And he seems to want to defend ideas even when he believes they might be wrong.
Yes. Yeah, that's an interesting point, and I think it still deserves some historical and philosophical investigation, and not fully clear on when and how Feyerabend developed uh, pluralism. But I think that for sure this is kind of a knowledge from many historians of physics, at least. Um, it was through really the ideas of foundations of quantum mechanics that Feyerabend gets a way of the falsificationism theory of Popper. So the fact that there is a normative way of telling apart good science from pseudoscience, telling apart that there is a correct method that scientists are using and ought to use. And I think that this is really having understood better. So he studied better Bohr's ideas, and he thought that these were a good way of portraying a picture that can nevertheless be told in a completely different way and still make sense of it. So this monolithic view that Popper has, that there is an objective reality, and that, so in Popper's work perhaps, that there is truth, and that our theories are approaching truth via elimination of the falsified models. This idea that there is really this monolithic single view to which we have to aspire, I think that's where Feyerabend gets this. He gets this idea from exactly the pluralism of interpretations of quantum mechanics, that they coexist and give different parts of the story, complementary and yet not exclusively. I agree with this. I agree with this. And yeah, but still, so I think that these. So I think it's interesting to summarize my view on this debate between Popper and Feyerabend, because I think what is known to the general public, this is very, very well known, even outside of philosophers, even outside of academics, is quite known, these ideas of the main contributors to the methodological debate in the last century, and everybody would mention Popper, Popper, Kuhn, Feyerabend probably are the three names that will resonate always. And the Popper-Feyerabend debate is usually really seen as, yeah, Popper has a methodology, Feyerabend destroys it, and that's it. But I think that this is just the arrival point of a much vaster campaign that Feyerabend fought, starting from quantum mechanics. So the first rebellion starts within Popper's ideas on quantum mechanics and within their personal relationship. So Feyerabend had a need of independence, of not being regarded as a Popperian. He had the need of become his own man, to have his own ideas as a philosopher, to be regarded as an independent from the school of Poppers. And only then he starts thinking at the big picture level, and he starts really going into the methodology. But I think that what is important for this story, why the debate on quantum mechanics between Popper and Feyerabend, it's important. Why it's important, their contribution to quantum mechanics, is also because, I claim, this causally influenced their debate on scientific method. So
that, yeah, no, it's a fascinating point, and I hadn't made the connections between physicists like Bohm and Feyerabend before reading your paper. We have to have our last few minutes here to talk about the 1980s, and you've written another paper about the 1980s, and of course we're going to have to take some big brushstrokes here. But you write that the Irish physicist John Bell, after a decade where this is a lot of the discussion around the issue of foundation of quantum mechanics is largely theoretical. The first reliable test comes forward, and this reinvigorates the field in some way. And Popper is back in the 1980s here, June 6, 1980, and he proposes an EPR experiment. I'll get you to explain what that is.
yes.
Which I believe he thinks is successful, will actually contradict the Copenhagen interpretation, or at least show that it's incompatible with quantum mechanics.
Yes. So this is the third part, we can say, of Popper's engagement in quantum foundations, quite unrelated from the first two, in the sense of the protagonist of this part. And it is Jean-Pierre Viget, a physicist who was a student of Louis de Broglie, and um, and Franco Selleri, an Italian physicist who was the one who initiated the revival of quantum foundations in 1960s in Italy, who became acquainted with Popper, I believe through David Bohm, because they were realists as well, and they were highly regarding the hidden variables theory of Bohm as very important. And and indeed, Popper here proposes really a physics experiment. So that's the first time well, there was the flowed experiment in 34, but that's the first time that is not just a conceptual contribution, but it has a modification of this Einstein, Podolsky, and Rosen, EPR, thought experiment, which is a thought experiment proposed by Einstein, Podolsky, and Rosen in 1935 that became very famous because it's the first time that you can see what is called quantum entanglement at work. So quantum entanglement is a form of strong correlations that particles can have. So imagine two coins, and every time you toss your coin, and you have two coins in the same place, and then you separate them. So imagine I keep a coin, and you have another coin on the other side of the planet, and I toss my coin, and I see it's heads. And if you look at yours, it's also head. Then I toss my coin again, it's tails, and you see your coins is also tails, and so on. So the coins are, although these are random objects, and I cannot send you a signal through this. I cannot decide to send you a message because my coin is anyways random. I cannot control whether it falls heads or tails. But every time it does head tails, yours also is tails. Every time my coin is heads, your coin is heads. So there is these very strong correlations. And this is something that is not achievable in the classical world, but that is theorized by quantum physics. So in quantum physics, you can prepare states of particles that have this feature of having these correlations. And 1935 is the first thought experiment using this to show. So Einstein, Podolsky, and Rosen wanted to show that quantum mechanics is not complete. That there must be something that tells these coins to coordinate. They cannot be that because they call this spooky action at a distance. If there was nothing, right? If there was nothing telling how the coins know how to coordinate. There must be something that travels from one side to the other. And therefore, the theory is not complete because it's not describing this signal that travels from one side to the other. Okay, nowadays we know that this is not problematic because what I just told you, you cannot actually send a signal. And yeah, but Popper devised modification of this experiment where you have still two particles, they're also correlated, and then you put a narrow slit on one side and you expect the particle, because of what I told you about the Heisenberg uncertainty principle at the beginning of the interview of the podcast, you have like this narrow slit means that you know the particle's position very well. Therefore, its velocity becomes very much unknown. So the particle can end up in basically anywhere. So you lose control over the particle if you localize it very well on one side. Since you have this other entangled particle on the other side, Popper says, if you also have a slit, it must behave the same way. What happens if I remove the slit? And then he claims that Copenhagen interpretation would tell that removing the slit would nevertheless lead to the spreading of the wave function. So in the same way of the spreading of the particle, in the same way as if the slit was there or not. Therefore, having or not the slit would allow to not change the behavior of the slit. It's only on one side that tells you whether the particle ends up in the same position or not. What does it mean? It means that what was proposed by Popper is that there is an interpretation of quantum mechanics, the Copenhagen one, the standard one, that predicts one outcome, and there is the realistic interpretation that he was advocating that predicts a different outcome of the experiment. This is what the way Popper put down this. So this is really an experiment that can tell apart a realistic interpretation versus the Copenhagen interpretation that he was criticizing. And this was had a certain influence. Physicists were very excited. He spoke in conferences. He did publications. He really entered full-fledged what my friend, historian of physics from Brazil, Olival Freire Jr. calls the quantum dissidents. This bunch of physicists who were criticizing the orthodoxy of quantum foundations in the 70s and 80s. So Popper becomes really a quantum physicist, a quantum dissident in the community of physicists.
And
Okay.
Yeah, so I'm going, please now continue.
Yeah, no, just end of the story is that the experiment was actually performed in 1999, unfortunately after Popper's died. And they found out that Popper's prediction was correct. This caused a certain stir. The two experimentalists, Kim and Shi, who did this, were not able to publish it in any good journal because people were saying, this looks like a violation of quantum mechanics. Nobody wanted to take responsibility to actually put out a paper. What if it's wrong, etc., etc. So it's interesting also from the historical point of view, from the methodological point of view of how science works, right? Like you find an experiment that violates our best theory, and journals like Physical Review and Nature didn't want to publish it exactly because of this.
So just to clarify,
Yeah.
so there was a period there we should brush over just for time where Popper is in his last years desperate to get this experiment done, and then it gets done in, as you said, in 1999 after he's already passed away.
Yes.
And correct me if I'm wrong here, it produces the exact result that he predicts, and yet
Indeed.
the two experimenters say it's not a violation of the uncertainty principle, though.
Yes.
So
yes.
how does that? Yeah, please go.
Yeah. So that's the resolution here, is that indeed the particle. So indeed the experiment had the results that Popper predict, and people were very shocked somehow that this was the result. On the other hand, it turned out that the opposite result that Popper predicted was wrong, in the sense that under any interpretation of quantum mechanics, this is what would happen. So somehow what was wrong is that the experiment what was wrong in the experiment is that the result of the experiment could tell apart the two different interpretations. Both interpretations are predicting the same result. So the prediction of Popper was correct, but also the prediction that Popper claimed was opposite was actually the same. This is the resolution of the, and nowadays we know. But what's the take-home message here is that still in 1999, when this experiment was performed, it was not clear to physicists. So we were like quantum mechanics was 80 plus years old, and still physicists, the whole community of physicists, could not spot the mistake into the idea of Popper that Copenhagen interpretation would not predict that particular outcome. Quantum mechanics is a very fascinating and very difficult subject, and sometimes it's so confusing at the fundamental level that it took us decades and decades. Now we are almost a century into it, and we still have experiments of this kind that we're not able to understand fully until they're performed. And then in the case of Popper's experiment, after it was performed and the whole theory was at stake, people did spend enough time to understand what was the mistake. And indeed, there was a. I want to stress again, it was not a technical mistake. It was really what people thought quantum mechanics would say about this experiment, and it was not saying that.
What do you make of I suppose that goes some way to explaining the response of the reviewers. So they try and get this result published. Kim and Shi, I believe the names are.
Yes.
And of course, everyone has gripes when they don't get their academic papers published. But these gripes seem. I'll read a few out, and I'll get you to perhaps tell us
Yeah.
how we should see them. So this is some quotes. I think this is from Shi. So they send the paper in, and this is the response. This is, quote, "This is a violation of the uncertainty principle. It can't be published. It's basically wrong." And then the response to Kim, who this is from Nature, said, "Well, basically all the referees said they just don't like Popper's idea at all. They don't care what these formulas do. They just don't like it." And then there's another one. I think this is She again. And speaking, "I've been given talks on Popper's experiment for the last three conferences. Most of the people don't believe it. They just don't believe me. They said there must be something wrong here." So how should we view that response of the field? Is this a normal enough response, or was there something odd with this?
Well, it's not a normal response because it's not very normal to find the violations of a so much corroborated theory like quantum mechanics. So it's rare. We had one a few years back. It was, I think, around 10 years ago, when they found that neutrinos might travel faster than light, and there was a big stir about this in the physics community. So sometimes you find, well, these are falsification experiments. Now, if we're talking in Popperian terms, like this is what science is supposed to be according to Popper, to find these experiments and perform them and find a falsification and throw away quantum mechanics. So what I make of this is, I would have liked Popper to be alive and see this and see how it would comment on it.
Mm,
My comment is that science, well, the falsificationism is not so easy, right? So we use it on a daily basis. It's the way we like to look at ourselves as scientists, to falsify, to propose experiments, conjecture, and refutations on a day by day. But the day that you really find that you crack quantum mechanics, are you really throwing it away that very day? I understand that there is like a strong core of resistance to this, because you want to double check 1,000 times
hmm
before you actually put to the stake quantum mechanics. So perhaps is more a Lakatosh way of you really need to have a very big amount of falsifications once you reach the point that the research program is regressive. Then you consider a further theory rather than the single experiment to falsify the theory.
Mm,
I think there is like a long inertia, right?
yeah.
That's the
Well,
what I would say about that. Yeah.
I've kept you longer than I promised, but I just one last question then,
Sure.
and this might be a little broad, but I'll start with a quote here, and this is Popper when he's 90 years old, and he's still talking about about quantum mechanics. He says, I'm getting extremely old, but I still have new and exciting ideas in various fields, and I'm happy." And his output certainly diminished, certainly in as it was targeted towards quantum mechanics in those later years. But how should the field, how should we view Popper and his interactions and his input and his, I suppose, how he affected the field? Because at some point in your paper, you said a lot of this has been forgotten, and you did a lot of research digging up an awful lot of correspondences and papers and letters and private emails, and it took a tremendous amount of work, some of these papers of yours, and I wonder how you see it now, looking back on Popper's place within the field of quantum mechanics.
Yeah. Thanks. It's a very good conclusive remarks that I would like to make indeed. Um, yeah. So the quote I found fantastic. The quote that you just mentioned. I closed my first paper on Popper, I think, with that quote because this really tells how was the personality of Popper of being like it was inexhaustible in his he saw this really as a mission and um, yeah. So what do we make of Popper's ideas on quantum mechanics? The thing that I admire the most it's his perseverance and his coherence. Not only so, I see that his ideas on quantum mechanics are very coherent with the ideas he had in every other discipline. This idea of realism, the idea of an open future that would allow humankind to be better than it was and it currently is. So this is very admiring. Going more into the content. So we cannot say that Popper's contributions were scientifically groundbreaking. So most of the things that he um, proposed were eventually ruled out or based on misconceptions. So he did not put forward an idea that has gone down into the textbooks of quantum mechanics. This we have to be honest about that. But on the other hand, I think that Popper played an immense role as part of these few people who really acknowledged the existence of a problem, of a conceptual problem, of an interpretational problem, of the fact that we use this theory of quantum mechanics, but we have no idea what is it talking about. And Popper has been a great, great fighter in these efforts of putting out this problem. He has, meanwhile, developed a new interpretation of indeterministic theories through these propensities that still has not a huge, but quite an impact on scientific works, on mine for sure. It has been an incredible connection between the philosophical and the physics community at a time where philosophizing was considered. It was the time of shut up and calculate. It was the time where physicists were like completely prevented from thinking in a deeper sense. They were just supposed to use their theories. So Popper has been like I think an incredible influence um, in this effort of trying to connect with physics, connecting physicists and philosophers. Something that we still nowadays are experiencing much better, but we should do more to fight together the same. We are talking about the same things. We just have from different approaches, and it can only be good to tell each other what we think about the same problems. And finally, I think also this idea, this debate with Feyerabend, which is, as I said, most well known, acknowledging that this stemmed from their debate on quantum foundations is very important because it really at the historical level can show that it's discussing certain ideas that can trigger general ideas on the philosophy of science. Discussing the specific contents of scientific theories has led the disagreement with Feyerabend and Popper that has shaped completely the philosophical views on scientific method in the 20th century. So these are like the main contributions. So I think it's still not fully reconstructed, but the impact of Popper, both as a single author and as part of a thought collective, has been huge and should be considered much more.
That is a wonderful note to end the podcast on. I'm going to link all three papers that Flavio has written about those three different stages of Popper's interaction with quantum mechanics. And I'll link the paper that we mentioned briefly at the start about an indeterminate past as well as a future. And I can't encourage listeners enough to go and read them for themselves. Flavio Del Santo, it was such a pleasure. Thank you so much for your time.
Thank you very much for having me. It was absolutely a great pleasure for me as well.